Okay, so in this problem, we're asked three things. We've got a circuit that has a fully discharged capacitor in it. We've got a switch there that's going to connect the capacitor and that resistor network to the voltage source. And that cap is going to charge up to something. So we're being asked, how long will it take to charge the cap if it's fully discharged after the switch is closed for 5 tau? And then what will the cap charge up to after 5 tau? And then what is the voltage on the cap after the switch has been closed for 10 milliseconds? Okay, so notice here that the cap is in this uh, network of resistors and things. So we need to simplify this circuit so we can figure out what voltage the cap is going to charge up to and how long it's going to take the cap to charge. So we need to find the Thevenin equivalent of this circuit right here. So the first thing I'm going to do is I'm going to remove the load. And for this example here, I'm just going to make the switch closed. So there it is. It's closed. 180, 47, 120. So there's 180, 47, 120, 220. Here's where the capacitor was. This one's 330. That's point B. That's where the cap was. And this is 12 volts. All right. So I've removed the cap. Now I'm going to Thevenize this circuit. So the first thing I'm going to do is I'm going to find R Thevenin. So I need to turn the circuit off to do this. So to turn off a voltage source, I just short it. So I'm putting my thumb there. That means I've shorted it. So notice that 120 and 180 are in series with each other here. So they're going to sum together to be 300. And they're in parallel with 47. So 300 times 47 divided by 347 is 40.63 ohms. And that 40.63 there is in series with 220 and 330, so that's 550. So plus 550. 590.63. Here's our Thevenin equivalent. 590.63. So that's R Thevenin. Let's see what V Thevenin is. So I know that the current is just flowing like this because there's no path here, there's no path here. So these are just basically out of the circuit. So I just need to know what is the voltage across the 47. Well, that's easy enough to do. We know that around this loop here we've got 347 ohms. So 12 volts times 47 over 347 gives us what? 12 times 47 over 347. That gives us 1.62 volts. Across there, there's no drop across that. There's no drop across that because there's no current through them. So that means this is going to be 1.62 volts right there. And if we connect the capacitor back into this circuit and we hold that switch down, I guess the switch would be right here. In this case, we hold that switch down, it's going to charge this capacitor up to 1.62 volts after 5 tau. So 1.62 volts is the answer to part 2 there. How long will it take the cap to charge if the switch is closed for 5 tau? Well, that's going to be 5 times R times C. So C is 100 microfarads. All right, so 0.0001 times 590.63 times 5 is 295.3 milliseconds. me just check my work there for a second. Yeah, that's what it's going to be. So it's going to take this capacitor 295.3 milliseconds to charge up to 1.62 volts in this circuit. So it's going to be 295.3 milliseconds. Okay. So then I'm asked, what is the voltage on the cap after the switch has been closed for 10 milliseconds? Well, let's use this model here. I'm going to redraw the circuit. So 1.62 volts is right here. Here's our switch. Here is the resistance the cap is seeing in this circuit. So that's 590.63. Here is the cap. All right. And it is 100 microfarads initially discharged. And then the switch closes. Well, we're going to have to use our charging cap formula, which is the voltage on the capacitor is equal to the charging voltage, which in this case I'm going to call Vs, times 1 minus e to the negative t over tau, or RC, however you want to put it. Let's just call it tau in this case. And what is tau in our circuit? It's just going to be 590.63 times 100 microfarads, which is 59.063 milliseconds. So that is what our tau is, and that's what we're going to plug in right there. So we're trying to solve for t. So let's fill in what we know. Well, actually, we're not solving for t. We're given t. We're trying to solve for the voltage on the cap. I'm sorry. So it's going to be voltage on the capacitor is equal to the charging voltage, so that's 1.62 volts, times 1 minus e to the negative. And how long has the switch been closed? 10 milliseconds. So negative 0.01 divided by 59.063 milliseconds right there. So let's see. 1.62 times 1 minus e to the negative 0.01 divided by 0.059063. Close the parentheses. And I am getting 252.3 millivolts. And put that up here. 252.3 millivolts. Does that all make sense? Well, I guess I can take this opportunity here to check my work. And this would actually be a good example for another type of problem anyway, where I say the voltage on the cap is this, so how long must the switch have been held down for? So that's where we solve for t. So let's do that. So we'll say 252.3 millivolts is equal to 1.62 times 1 minus e to the negative. And this time I'm just putting t because I want to solve for that. It should come out to 10 milliseconds if my calculation is right. So 59.063, and that's milli right there. So let's do the algebra. So the first thing we're going to do is we're going to divide both sides by 1.62. So 0.2523 divided by 1.62 is 0.1557. So 0.1557. All right. And that leaves us with 1 minus e to the negative t over tau right there. So let's bring the 1 over to the other side. So we're going to say this minus 1 equals negative 0.844 equals minus e to the negative t over, I'm just going to write tau right there. Okay, so now we've got this. So we get a negative on both sides. I'm going to make that positive. There we go. And then I'm going to take the natural log of both sides. So ln of 0.844 equals, and that's going to make the e go away, and we're going to say minus t over tau right here. And so let's see what ln of 0.844 is. It is minus 0.1696. I'll carry that extra 6, I guess. And that is equal to negative t over tau, which is 59.063 milliseconds right there. So notice we've got a negative on both sides again. I'm going to make that positive. I'm going to multiply both sides by tau, so that tau is going to go away. So let's do that. Times 0.059063, and that is giving me 10 milliseconds right there. So that means that my answer is correct here. That is, it is going to be 2.5 or 252.3 millivolts when the switch has been closed for 10 seconds. All right, so that was a pretty good capacitor workout. I think that does it for this video.